In this video, we'll look at how to combine functions in several ways. The first is addition. The second is subtraction, to go with the addition. The third is multiplication. And the fourth, to go with multiplication, is division. And there's a fifth one, which we'll talk about towards the end, called composition of functions. And it's a little bit different from the other four. And then the other question that we're going to ask for all five of these things is, what about the domains? So if you take two functions and add them or subtract them or whatever, what does that say about the domains of those functions? So first we'll look at addition and subtraction. They're easier. So we'll need a couple of functions to work with here, just sort of as an example. So I'm going to choose f of x to be 6x minus 4, and g of x will be 2 minus x. Okay, so those are our two functions. And then we're going to add them and subtract them and then figure out what the domains are going to be. So the first question is, what should it mean to talk about adding them together? So we're going to construct a new function, which we'll call f plus g. And if you plug an x into this new function, how do you compute it? Well, how do you think? You just take f, plug x into it, plug x into g, and then add the two answers together. Now for our particular functions, 6x minus 4 for f and 2 minus x for g, that gets us 5x and then minus 2. So that's f plus g. Similarly, f minus g is going to be almost the same thing, except this time we subtract. So the value of f minus g at a point x is f of x minus g of x. Just evaluate the two functions separately and then subtract. So for us, we have 6x minus 4, and then we need a minus right here because we're subtracting, and then we're subtracting g, which was 2 minus x. So here we simplify, and we get, careful with the double negative, actually 7x and then minus 6. Okay, so then over here on the right, let's figure out what is going on with the domains. So for the domains, we have to also worry about what the domain of f and g are individually. For the example we have here, they're all real numbers. So in order to plug in something to this new function f plus g, you have to first be able to plug it into f and then separately be able to plug it into g. Okay, so what we're going to write here is that the domain of f plus g is the domain of f and the domain of g are both relevant, and then in order to plug in, you have to be able to plug into both f and g, and that upside down U is kind of the math symbol for and. The technical term is its intersection. Okay, and then the subtraction case is really just the same thing, so that has the same domain. So whatever the domain of f is, intersected with whatever the domain of g is. Okay, so we've used previously the upside down or the right side up U to mean or. Okay, so the word intersection should sort of conjure this kind of picture for you. So let's say that we have the domain of f is the small circle, and then the domain of G is this other circle. Then when we ask what the intersection is, it's the stuff that's in both circles. So the domain of F intersect the domain of G is the stuff that's in both sets, and that's what we need here. Okay, so now we'll look at the multiplication case. So again, we'll use the same pair of example functions as we had in the last two examples. F was 6x minus 4. G is going to be 2 minus x. So the new function we're going to define is called fg, so the product of the two functions, and we define that by literally doing f of x times, or times not plus, I'll correct that in a second. There we go. And so here, f is 6x minus 4, g is 2 minus x, and so we just multiply them, and that requires a little bit of foiling. So we get 12x minus 8 minus 6x squared, and then plus 4x. Then just do a little bit of simplification here, and we get minus 6x squared plus the 16x, and then minus 8. Okay, so computing that was pretty easy. Now, the f over g case at x is literally just to take f and divide it by g. Okay, and in this case, so we have 6x minus 4 on top, and then on the bottom, 2 minus x. Now, in this case, there's no simplification we can do, so that's it for writing it down. Okay, so now over here on the right, let's consider what the domains of these two functions are going to be. The multiplication case is going to be very similar to addition, because to multiply two numbers, you have to be able to well, have numbers in the first place. So the domain of f and g is just like with addition and subtraction, the domain of f intersect the domain of g. Okay, so that's no different. Division case is a little bit more problematic, though. Now, at minimum, we still need to have the domain of f intersect the domain of g, because you need to be able to plug in x to the function f, x separately to the function g, and then we do some division. So to even get started, you first have to be able to plug it into f and g. So we'll write that down over here, and then leave a little bit of space to the right, because we're going to need something else. Okay? And that something else is going to take into account the fact that we have a potential problem with division. Namely, if we plug in something that makes g of x equal to 0, then we might have a division by 0 kind of situation. Now for our function g, the only thing that you can plug into g in order to get 0 is when x is 2. Okay, so that's sort of a problem if you try and plug that in. And there's no problems with plugging in anything in particular to f. It's okay to have 0 in the numerator. Okay, so what we have to rule out here are any values that make the denominator equal to 0. And then we need to dispose of them somehow, so we need to use a special symbol that basically says to subtract sets. Okay, and the symbol we're going to use for that is a little slash, which I'll write here in a second. And it's the slash kind of like this. So all that means is take things in the set on the right and take them out of the set on the left. Okay, so take the domain of f intersect g, and that's a big pile of numbers, and then throw out of there anything that makes g equal to 0. Okay, now in our particular example, that was just x equals 2. So for our example, the domain of f is the set of all real numbers. The domain of g is also the set of all real numbers. And the set that makes g equal to 0 is, in this case, just the single element 2. That's the only number that makes g equal to 0. So there's only one thing in that set, the number 2. Okay, so the domain of the intersection, or excuse me, the division is, as we said before, the domain of f intersects the domain of g, and we'll figure out what that is in a second, and then we need to throw out the number 2. Now, anything intersect itself is just itself. Okay, and that should be relatively clear. Basically, that's when the two circles overlap completely. And so we need to take 2 out of the set of all real numbers. Okay, so this is all reals except 2, if we write it out in words, or in symbols, it's that. You could also write it as an interval. So the last thing we'll look at is how to do composition of functions. And this is basically plugging two functions into each other. Okay, so we need a new set of example functions, so I'll use f of x is 3x plus 9, and we'll use g equal to 9 minus x. Okay, so just new set of functions here. Okay, so the idea behind composition is this. If you've got two functions, functions have domain and a range. Okay, so let's just say that one function, f, takes us from the first circle to the second circle. Okay, so it's has domain on the far left, and then its range is in the middle. And then there's another function, g, which takes us from the middle circle to the right-hand circle. And basically what we're asking is there a function, a direct flight, if you will, that takes us all the way from the first circle to the last circle? And that function that's going to do this, we're going to call g composed with f. And I'll define what that means here in a second. So g composed with f is defined to be, and this is a little backwards from what you'd think, it's f of x on the inside, and then we apply g to it. Okay, so we're plugged f in to the function g. Okay, so for our specific functions, what are we going to have here? We'll have g of f is g with f plugged in. F was 3x plus 9, so that's what we're going to substitute in. And then what does g do? It takes a thing and then subtracts it from 9. So g of x is 9 minus x. G of some stuff is 9 minus the stuff. Okay, and then now we can do a little simplification. So we get 9 minus 9 is 0. So in this case, we just get negative 3x. And that's it. Now, here we did f first and then applied g. But there's no reason that we couldn't have done it in the other order. So we'll look at that here. What about if we had done g first and then f? Okay, so just kind of switching the roles of f and g, the letters. So f composed g will just be the other way, and that means that g goes on the inside and f goes on the outside, so it's f of g instead of g of f like in the last example. Okay, so now let's figure out what that is for this example. It's f of g. G is 9 minus x. So we'll do f of 9 minus x. And then what does f do? It takes a thing in, multiplies it by 3, and then adds 9. So f of 9 minus x will be 3 times 9 minus x plus 9. And now again we simplify. So we get 27 minus 3x plus the 9, and then that's so a total of 36 minus 3x. Now in class we'll talk a little bit more about the domains, but for now just notice that the order really matters here. In general, f composed g is not the same as g composed f. Now for special functions it actually is. We'll talk about those actually for the next section. But for now just keep in mind that in general they're not going to be the same. Now figuring out what the domains of these compositions is actually a little bit tricky, so that's something I'm going to leave for the discussion in class.